There we go. Oh, did you guys want me to cast out? There you go. You should have it as a window now. Yeah. So we're going to look at this problem number 9, the problem set. And in this case, as in all these cases, we can take for a fact that the object, the person, whatever we're talking about in it, is in static equilibrium. Remember, what that means is that the torques are balanced about any point, and the forces are balanced about any point. So we have both of those to consider, and they must be balanced. In this one, they tell us ignore the mass of the ladder, which actually simplifies it a lot, and assume the ground is frictionless, which again is simplification of this force. And then they tell us consider free body diagram for each section of the ladder. So what we're going to kind of assume is that the ladder, we've got, 3 points of contact on each thing, here, 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 and here, where we need to consider what's going on. Now, at the very bottom, what must we consider about since it's frictionless, at those 2 contact points with the ground? The only force can be a vertical normal force. There can't be any sideways force there, because the only thing that can provide that sideways force would be friction. So the normal forces that happen at the bottom can only be vertical, which means, therefore, any horizontal force that takes place at the halfway point has to be balanced by an equal and opposite horizontal force from the top point. So that's kind of letting us simplify things. So let's first do this side of the ladder, and yes, I'm exaggerating it, and then we'll do it in a different color. We'll do this side of the ladder. All right. So let's see. The bottom, let's call that force normal 1. At the top, I'm going to say that because I'm picturing these two pushing against each other at the top, there's going to be, I'm going to say, force normal top, and I'm going to guess that there's going to be a force normal top y. We'll call this x. On this one here, there's going to be, of course, the weight of the person, and then there's going to have to be, there might be a downwards force here, but there probably is going to be a force in this direction here. So let's call that force middle x and force middle y for the left-hand side there. Now, some of those forces may end up being 0, but I'd rather assume that they were there and then work them out to be 0 than assume that they're 0 and end up stuck because I didn't think they were there. So here we go again. This would be force normal 2. At the top here, I'm going to guess that there's a force normal top y2. Wow, that's getting messy. if there's actually going to be those at the top. What do you guys think? The top of the ladder. Yep. And my guess is they don't exist. And I think I'm going to assume that there's no vertical force at the top. Yeah. Well, let's think about it. Could there be on the blue side, could there be force? Well, see, we could have this one, right? But we can't have any horizontal at the bottom. We have a hinge in the middle. A hinge in the middle should just be horizontal. And then we would have to have one up here, but it would have to be in the other direction. But then, I'm taking the simpler case first. Then, if this is being pulled this way by the mx2 to balance that, it would have to, those two could create equal and opposite torques if we took the top to be around the torque, right? Because this one would cause clockwise, this would cause counterclockwise. And these two could balance out horizontally, and these two could balance out vertically. And that would get rid of our need for any horizontal force at the bracing point. And if we think about the ladder, if we're standing on it and it doesn't have the brace, it's going to go straight out, right? So the brace is providing the horizontal force, right? No, I'm saying that there's no vertical at the center brace. That's the assumption I'm going to go with. And the need for the vertical on the in the interior to be up and down like it is. What if we did it for the whole thing, though? We would have, let's see, FN2, right? And FN1, and then MG. We did the whole thing as a whole, right? Right, that's the mass of the person. And those are going to be different sizes. So let's deal with the whole thing and then deal with the individual parts. Stands 2 meters from the bottom of the step ladder in the figure showed. And the whole thing is 2.5, right? So let's do a little angle. So this is 0.9 and this is 2.5 and this is 2, right? So 4/5, right? No. So So this should be 4/5 times 0.9. Similar triangles? Yes? So I'm going to do two things over here. Let's see. I'm going to do the sum of the forces equals 0. And this is going to be for the whole system. And so that's going to be that Fn1 plus Fn2 minus mg equals 0. And then I'm going to do the sum of the torques equals 0. Because remember, that's my other static equilibrium condition. Yes? And I'm going to do that around the bottom of the ladder here, around this point here. So if I do that, then the weight is causing a clockwise torque, and F2 is causing a counterclockwise torque. And so my clockwise torque is going to be my negative torque. So that'd be negative mg times, it's working at that 4/5 0.9 distance away. That's why I did that little similar triangle thing there. Plus my clockwise torque, which would be Fn2 acting at 1.8 meters away. And that's going to equal 0. So I've applied my two equilibrium conditions. And I didn't even look at what did they ask us to solve for in this one. Tension in the tie rod. Okay, so maybe we'll save that one to do. Magnitude of the normal towards the ground on the left side. Okay, so we're about to do the right side and the left side. All right, so let's see if this works out. Considering it is Monday, I am sick, and we just got back from break. So 72 kilograms is the only thing I need in here. So good old mathematical manipulation, and I'd end up with my calculator someplace. Line 72. So I got 282. Does that work? That work for you? Excellent. So this is the right side, right? So, and my answer was actually 282.528 newtons. I did the math here knowing that my M was 72 kilograms. I solved in the sum of the torques because I only had the one variable. And now actually I'm going to go back up and use the whole system and solve for N1. So I'm going to, so now it'll be Fn1 minus mg equals my 282.528 newtons. So I get 988. Where's that? Nope, wait a minute. Oh, that'd be negative. Yeah, now I'm doing the right side. And I almost made a little math mistake. That was mine on the right-hand side. And then I get FN1 is 424 newtons for me. Provocative. Oh boy. All right. Any questions on that part before we go on to do the tension and the velocity stuff? All right, so moving on. So all the blue here is that first is the whole system diagram. And this we did is this was our pivot point. And then now we're going to go on and try to work on finding the force in the hinge. All right, and I'm going to use the right-hand side of our ladder for that. All right, so I'm going to go down here and I'm going to, I'm going to use the right-hand side. And I'm going to start off by looking at the torques. Remember, the sum of the torques is 0. On all of these, I always kind of start at those equilibrium conditions, the torques and the forces. And for me, I'm going to take the torque about the top of this. All right. I know that the brace connects halfway, right? Hinge conservator. I think it tells us in the problem that it connects halfway, right? Tie rod, which is halfway up the ladder. So I'm going to look at my torques about the center point here. And so I need to say, okay, well, if I can either take the part of my torque that is perpendicular to the lever arm, or I can take the part of the lever arm that's perpendicular to the force to get my torques. I'm going to choose to do the part of the lever arm. So what I need to do is find this distance here and this distance here, because those are my two lever arms. Well, this one's easy. This is 0.9 meters. They gave me that one, right? And the other one should be just as straightforward, making a little mini triangle here where this is 1.25. That would make this 0.45. And then that side would be 1.25 squared minus 0.45 squared square rooted. This side is 1.1662 meters. And that would be the length of the lever arm up there. Right? Yes? No? Any thoughts? Yeah, I took a halfway up triangle, yeah. I could have also, figured out like the angles in here and everything like that. Just seemed easier to do it through ratios. So now, let's see, the normal force is going to produce a counterclockwise or positive torque. The force at the hinge here, or sorry, at the, what do they call it? Horizontal tie rod. At the horizontal tie rod is going to produce a clockwise or negative torque. So let's so the counterclockwise torque is going to be Fn2 times 0.9 meters minus what did we call that force? Force mx times the 1.1661 meters equals 0. So I did, and I know my force normal 2, it's right above there. So my FMX should be, let's see, 282.5. I got 218, which makes sense because it's a longer lever arm producing the same amount of torque, so it should be a smaller force. So logically, it's making sense. Let's see if we got lucky again on a Monday morning, afternoon, whatever it is, and we did. Yeah. So 218. All right, so for this last segment, we want to determine what the two components are here to determine the main force. We could actually do it. We know that the forces have to be sum up to 0 on this right-hand side, right? Therefore, if we add up the three forces, the normal one at the bottom, the FMX at the middle, which we just found, and the mg, we add those three up. The resultant there would be equal and opposite to the resultant to the force at the top of the ladder. So it's kind of redrawing this thing. I'm going to redraw the free body. So now we're looking. Oops, now we're looking at the left side. Let me just make sure. Is that what they asked? Actually, no. We can just do it. Oh, they made it easier. Determine the force on the left side of the ladder exerts on the right side, the hinge at the top. So the hinge at the top, if we looked at just the hinge, it would have to have a 0 net force on it also, right? So if we look at our two forces on the left side, the sum of those is going to be equal to the sum of the force exerted at the top. So we're going to keep looking at the right-hand side here, not the left, excuse me. We won't look at the left, we'll look at the right. And the way we're going to look at it is FMX, force normal 2, and then the force that we want after that direction. So those can equal out, kind of doing a simplified free body diagram there. And they want above the horizontal. So we're actually, this is the force that it reacts with, the force we're going to want is going to actually be in this direction with looking at this angle in here, theta. All right, so it's going to be this is the blacks are the forces on the right hand side. The force on the right due to the left would be the equal and opposite to this force F. It actually be the sum of those two together. So this last part is actually a lot simpler than it seems. We just do Fmx and Fn2, and we're looking for F and theta. And it's a good old right triangle, right? Yay! Give it a try. Let me see if I get it. You see if you get it. That was good, Ed. All right. Let's look at this, which I believe is number 8. And we have this pole, and we have it by a support cable, and a traffic light hanging from the end of it. And they want to know, let's see, tension in the massless cable. Oh, nice. They made it massless, so we don't have to worry about that. Could a cable actually hang horizontally in reality? No, because it always has some mass pulling down on it, creating that slight angle. No matter how hard you pull it, you cannot get it horizontal. Always going to be down a little bit, unless it's massless or in a non-gravitational field. There we go. Or in a gravitational field that points in the same direction of it, like a vertical down. There you go. Determine the horizontal component of the force exerted at pivot A on the aluminum pole. Determine the vertical component of this force. So it's having us look at those as horizontal and vertical components rather than combined. So let's see. Let's do a little diagramming right on here. There's going to be the weight of the pole, right? And then there's the weight of the traffic light. And it's going to be a tension in this direction. Given that, I'm going to say that there's going to be a force normal in the x direction in that way. How do I know it's coming out that way? Yeah. Right. And there's going to be a force normal in the y, and I'm predicting that it will also be upwards. We good? Yes. So the tension and the force normal in the x are going to be the same. And so we can actually, that we get that from doing a heading of some of the forces in the x equals 0, and we can right away write force normal x equals force of tension. And then we can say, oh, some of the forces in the y must also equal 0. And so mpg plus mlg must equal force normal in the y. Yeah, we have all the masses, so that should be pretty straightforward to do, which is good because we're running short on time. To find the force of tension, I'm going to take my pivot point to be about point A, because that way I get rid of 2 unknown forces, right? Fny and Fnx. And so now I look at it and say, okay, well, Ft is going to produce a counterclockwise torque. Remember the old pencil trick if you're not sure. And the 2 weights are producing clockwise torques. And the only thing I have to worry about is how far they're acting. So one axe here and one axe here. And let's see, they tell me the pole is 7.5 meters long, right? So that means this whole distance here would be 7.5 cosine 37 degrees. And this shorter distance here would be 3.75 cosine 37 degrees. Since it's half, I'm assuming it's uniform, so therefore its center of mass, center of gravity is in the center of it. So my counterclockwise torque is F sub t, and they nicely told me, oh, that was 3.8, adding through 3.80 meters minus mpg times my 3.75 cosine 37 degrees minus mlg times my 7.5 cosine 37 degrees. Oops. And that should do it.